Just about there, folks. Well, it looks like it's official. Welcome back, everyone. I want to start off with some announcements before we get too far into the introductions today. Probably the most important one is our first assignment has come due on January 23rd. So just for some more advice on turning in your assignment, you can turn in a hard copy right down here in class if you like. I'll grade it up in the traditional way, return it to you when I next see you in class. If you like, you could also just pretending this is your assignment, just take a picture of it or scan it, and then send it directly to my email address. I'll accept assignments that way as well, which is probably how most people in the online only section are going to be turning in the homework. I don't have an actual field for submitting homework in Moodle. I found that that's clunky and been unreliable in the past. So for a complete assignment, again, cell phone pictures are fine, scan things are just fine, and email direct to here, and you'll be all set. If you email me your assignment, I'll grade it up in a slightly non-traditional way. I'll just use a digital pen, convert it to PDF, and email your work back to you. It'll be as if you turned it in physically in class. Any questions about that, folks, on turning in assignments?
What do you do with the hard copy?
With these, I'm going to mark them up with a green pen instead of a green digital pen, and I'll bring these back to class and hand it right back to you.
Great.
Yep, you bet. Other questions or comments so far?
Hey, Michael, I just want to let you know, I think the page numbers on it are wrong.
The page numbers on which thing?
Yep. Like section.
Oh, you mean down
yeah.
here?
Yeah, I think.
Geez, I did realize that.
Yeah, it was like when I opened it up, it was the exponential and logarithmic equations.
So that's way off. Yeah.
Yeah.
Take a look at what happened there.
I think for assignment two.
Oh, so it was okay here, but it was on this one.
No, both of them. Because
both of them, all of them probably then. So probably this one's wrong as well. Well, for finding the problems, it should be in the end of that section. But let me make a really
I just checked the section and then did the sections exercises.
Perfect. You did it right then. But I'm going to make a note of correct page numbers, because that's definitely a distraction we don't need. Numbers, and this will be for trig assignments. I'm not too sure where I got those numbers wrong, but I'll see if I can get us on the same page at least, as far as that's concerned. Other questions or comments at the moment? Okay, thanks for mentioning that again, Hayes. I've got my trusty Post-it note, so I'll get these looked at and corrected when we come back in class. And anything I revise, we'll just see it converts to red if I make a revision. Well, that's our assignment one that's come due today. And again, the pattern of attack for due dates and all that kind of stuff is section 5.2 is not complete. We want to do a few more problems, but once it is complete today, it'll be a 1 week turnaround. The purpose for a week turnaround is it gives you an opportunity to work on it, maybe visit with, say, me in office hours, tutors, other students, that kind of thing. If you have questions, you'll have time to turn around and get those questions asked and finalize your assignment. But really, I'd say the best way to do this class is I would try to complete the assignment as fast as possible. These ideas have a shelf life, and the moment you start practicing with them, the longer you're going to finalize or solidify these concepts in your mind. And it's just going to make the assignment much, much easier to get through if you work on these as soon as you get your next available time. As a night class, that might not be today for everybody. It might be the next day, maybe even quite a ways away, but it's always the sooner the better. The 1 week turnaround is not meant to be a week-long assignment. It's meant just to give you that extra breathing room for asking questions. Well, that's our spiel about assignments. We're going to go back to section 5.2 just for more practice. And at 5.3, we'll define the other 4 trigonometric functions. First, any other questions or comments that we need to address before starting? Okay, let's jump back into section 5.2. First, here's our reminder, just kind of a warm-up to start off today. We define all of our trigonometric functions on the unit circle. So by unit circle, we mean this right here, x squared plus y squared equals 1, gives us the equation of a circle whose center is the origin And when we say unit circle, it means the radius here to here is 1. The most big takeaway then is, after we decide where the angle is going to terminate at a point xy, we pick coordinates x and y, and cosine is going to be the first coordinate x. Sine will be the second coordinate y. So once we have that down pat, evaluating the trigonometric functions is now mainly all about knowing which quadrant your angle terminates. We'll always have really good reference angles to support us. These things we memorize pretty fast, whether we're trying to or not. It's just going to seep into your mind. But we can extrapolate these reference angles to the entire unit circle. So these are the inputs that give you these kinds of outputs here. Those outputs repeat. These are periodic functions, so things repeat after a certain period. And so that's exactly what we're going to use. You use the repeating periodic nature of the trig functions to calculate things like this, say 7 pi over 6. Sine at 7 pi over 6 just boil down to finding the right quadrant. Here it is in quadrant 3. Outputting the right value from the reference angle. And let's see if we can take a peek. It was a pi over 6 for a reference angle. And so we were expecting the 1/2 for sine. The only thing we got additionally is the negative sign by knowing where the angle terminated. So we got negative 1/2 as our output there. Now we'll just practice a few more. So this next one, it wasn't in the notes, but that's okay. We can find a way to put it there. You know, Microsoft likes to fight a little bit with adding additional white space for no apparent reason. So let's make this one our part D. And let's see, let's go with a 5 pi over 6. And that means we'll do this evaluation. Cosine 5 pi divided by 6. And let me, just for a moment, let's also take these with us as we go to show how we're using the reference angles as we solve these problems. So I'll just park that down there. If this was an exam question, this is probably what I would do to start this off. I would just jot down a really fast unit circle at 5 pi over 6. Here's the thought. You've got pi right here. This is also 6 pi over 6, if you like. Move backwards 30 degrees, and that's where 5 pi over 6 lands, in this location. That looks more like a pi over 4. Diagram doesn't have to be perfect, but the more accurate it is, the better. Here's 5 pi over 6, finally right in this location here. Next thing we can say is, because we're dealing with cosine, this is going to be the x-coordinate. So from here, we project down, and whatever that number equals, that's our value. To me, that number looks like it's really close to, say, a negative 0.9. And when it comes down to 0.9s, for a pi over 6, a root 3 over 2 is about a 0.9 altogether. But since we're terminating in quadrant 2, this becomes a negative root 3 over 2. And that's the output for cosine 5 pi over 6. Negative square root 3 halves. Kind of a strange process, and it's honestly one of the weirder ways to evaluate a function. We're used to writing out, say, y equals x squared plus 3. Evaluate that, you just pick an x and calculate that out. But here, you come up with the angle to start, you find where it terminates, then you decide, is it sine or cosine? Get the right coordinate, and make sure you have the right sign, and that's the process. Strange kind of functions, but the more we practice with this, the easier it becomes. Any questions at all, folks, on getting that negative root 3 over 2? Okay, should we practice a couple more just for the sake of more practice? Okay, let's do a couple more. So let's call this part E next. Oh, question first in chat. So does the number before the pi not matter? Does only the number in the denominator matter when looking it up? Yeah, thanks for mentioning that. That's a really interesting or really important statement about this. It's pretty much that denominator we're looking for when we're thinking reference angle. Because it ends with a 6 down below, we're dealing with that as the reference angle. We know we need to involve root 3 over 2. Let me make that highlighting a little bit better for this particular problem. And we just decided, well, it ought to be negative because of that coordinate right there. But yes, that denominator pointed us to that angle, and we knew √3/2 had to be there. We're just deciding, is it positive or negative, essentially. That's kind of nice in a certain sense. Does that make sense for that question there, Alex? This table down here, this is a table that we would have to memorize for the purpose of an exam. So these reference angles would have to be memorized. And really probably the better thing would be, let's see here, where is it? 5.1, I think. If you've got this down, just the angles and radian measure, you pretty much have everything you need to know, because all of these angles and radian measure, once you have this table down, is going to give you all the pertinent values. So I would memorize this table here, memorize these angles around here, and then you're going to be all set. Well, other questions or comments at the moment, folks? Okay, let's now turn to part E next. Forgot what part we were on. Okay, so now part E. Let's pick an angle. How about, I have a couple here, 7π/4. I'm just looking for angles we haven't hit on as often. And we just did cosine, so we might as well do sine. 7π divided by 4. Now, first thing we'll do here is, I like that statement by Alex. It's all about that denominator when you're looking for reference angles. So that 4 in π/4 takes us here. We're dealing with the sine function. So we're looking at that value, although it's the same as the cosine one. We already know our answer is going to be √2/2. We just need to know what what quadrant that thing is in. So here's our quick sketch. And I'll leave this one up to the class. Any volunteers to say, which quadrant does 7π/4 actually terminate in? Quadrant 4? Absolutely. And here's the kind of thought to get us there. Let's use this pencil. Here's π/4. These go by odd amounts. Here's 3π/4, 5π/4. And then just as you said, it terminates in quadrant 4 right here at 7π/4. So we've got that angle there. Now it's a sine function. So let's imagine we didn't see the reference angles. Because we know it's a sine function, we're going to take this output. Compare that output here versus this one. This one was much further to the far, far left, so it ought to have been closer to a -0.9. That's a dead-on hint. It should have been negative √3/2. This one, that's more of a 0.7, if I'm roughly estimating, than a 0.9, negative. So this one should be negative √2/2, right there in that location. Let me use a different color just to make that pop out. So that just looks funny. Let me try one more time. Negative √2/2 is that location right there. So even without the table of reference angles, if we're familiar with these outputs, you can pretty much guess the right value for your problem. Negative √2/2, like we mentioned, we are anticipating a √2/2, but because we're in quadrant 4 and we're taking a sine value, we threw a negative in front of that one as well. Well, other questions or comments at the moment? Okay, and just as I think we stated this before, but just as a visual reminder, when you see this negative √3/2, that's roughly approximated as a -0.9. And when you see a negative √2/2, that's roughly approximated as a -0.7. That's enough difference to tell between the angles. Even if your circle is kind of wonky, you can still get a really good intuition on which one is which. The more you memorize, the more protection you have on getting just the right exact value. But this is definitely a process, right? So what we should do is definitely try it again. This will be our last one before we go to the next section notes. Any questions so far? Okay, so here's our part F. We ought to do a cosine next, just for practice on both. And one angle we haven't hit is 4 pi over 3. But we also haven't done a negative angle. Well, we have, but not today. Let's do cosine at negative 4 pi over 3. So that'll be our angle. Well, next thing we have to do is just plot that angle. And because the angle is negative, here's a great way to think about this. This whole table, well, it's really a unit circle. So this whole unit circle is going to flip across the x-axis. So here's where 4 pi over 3 was. It ought to land up here as a negative 4 pi over 3. So let's give this a try and see if it really works out. First thing I would do is put down a rough unit circle. Now, if we're dealing with a pi over 3, let's go look at the right location, the reference angles. We're expecting either a positive or negative 1/2. So now let's start putting down those angles. So if we go this direction, in the clockwise direction here, this would be negative pi over 3. Continue to go, this one's negative 2 pi over 3. And up here, this one becomes negative 4 pi over 3. Let's put that one in just so that it's apparent. These are trickier being negative angles. Here's negative 5 pi over 3. But this is the one we wanted, right at negative 4 pi over 3. It says to evaluate cosine. So right where this terminated, project down to the x-axis. This position on the x-axis does not look like a 0.7. It certainly doesn't look like a 0.9. I would guess personally, it looks like a half right on this graph. And it turns out, well, I almost got it right. It is a half, but I forgot my negative sign right here. Turns out we have the right value. We had the half. We just didn't get the sign. Well, I didn't either. I had to get it on the second pass through. So the whole thing looks like cosine negative 4 pi over 3 evaluates to exactly negative 1/2, negative 0.5. So that's the wild adventure of evaluating trigonometric functions. And this whole process of evaluating this, drawing out a sketch, or using the reference angles is a very common process. It takes a lot of work to get it down pat on the first couple weeks or first few weeks of the course, but we'll do it repeatedly. So by, say, week 4, 5, or 6, it's going to be kind of second nature. The more you can do to memorize these angles, this is of huge importance. It'll help out a tremendous amount. Well, any questions at all, folks, before we go to the next section notes? Okay, well, congratulations, 5.2 is done. That means we're halfway through chapter 5 already. That's kind of shocking. We're going to only go up to section 5.4. So what's next is define all of the trigonometric functions in section 5.3. So this due date right here is considered official. We finished section 5.2 today, so it's due a week away. These due dates, well, they're in flux. If we complete section 5.3 when I think we might, that due date will stay right where it is. If we take additional time, that due date will shift. It's always going to be directly 1 week after completion. Alex says, for the table, are there any other denominators or cosine and sine we should memorize? Oh, that's a great question. It turns out for this table right here, this is pretty much it. If you have this exact table down, there's never going to be weird angles that are going to pop out of nowhere, unless you're on exam 3, but that's when we open up the calculators for the course. So for the purposes of exams 1 and 2, it's pretty much going to be this right here, extrapolate around the unit circle like we've been doing on these problems below. Other questions about that at the moment? Okay, well, here's our section 5.3. Now, one thing that is sometimes a little bit rough in trigonometry is that there is a lot of memorization. The memorization is going to be more heavy in chapter 5 for us, because those are the core definitions of what is even trigonometry. We have to know how cosine is defined. We have to memorize it, as well as sine and all those kinds of things. And when we get closer to this exam date, I'm going to start dropping in files right under where it says exam one. I'm going to specify the exact coverage, which section. I'll give additional problems to study that you could take a look at. And I'll also include a file that tells you what will be pasted onto your exam, the formulas that you don't have to memorize, and the things that you should memorize. There'll be an additional document there. So you'll know always exactly what's expected for memorization and what would be provided. Those are the things you just have to be familiar with. Well, starting this section off, it says if the terminal side of an angle T intersects the unit circle in a point XY, then we define the trigonometric functions in this way. This is really just review right here. Sine is still going to be the second coordinate, Y. Cosine is going to be the first coordinate, X. And then here's how the next definitions go. It turns out tangent, cosecant, secant, and cotangent are all defined in terms of X's and Y's, sine and cosine, in other words. But these are brand new functions and they have been abbreviated. So let's actually write some of these out. When you see sine, that's just an abbreviation for sine, the sine function. When you see cos, that's an abbreviation for the cosine function. We sometimes call that a cofunction. So cosine is just a way we say the cofunction to sine. Tan is abbreviation of tangent. I become less familiar with the history of these names once we get to some of these. CSC, that's a cofunction because it starts with C, and it's co to the secant function. If you see a CSC, this one is an abbreviation for cosecant. Let me spell it right first, though. Cosecant. Next, that's the abbreviation for secant, SEC, is secant. And last, when you see cot, that starts with C, so it's another co-function. It's co to the tangent function. So cot is just an abbreviation for cotangent. If everyone said cotangent, then it's obviously kind of specify it's co to this function, but we usually just glom it together and just say cotangent. Likewise, this one's cosecant, and this is the cosine. So that's really not anything additional new, but if you hear me say cosecant, it's good to know that I'm talking about that function. So that's the purpose of the notes here. Next thing we could do is, let's put down a unit circle just to tie together these portions of the definition. We want an angle that can terminate randomly just somewhere. Let's put it maybe here. They're using T, so we'll specify an angle T right here. It could have been rotated in the counterclockwise as a positive angle or clockwise as a negative angle, but we'll just specify it this way since the actual direction or the sign of it is not as relevant. So there's our angle T. We get a point XY, and that's where X and Y are coming from, the sine and the cosine function. So everything you see right here is pretty much how the book likes to present all of their 6 trigonometric functions, but I would propose a different kind of organization. I still like how it's written out here, but for the purposes of actually working with these things, not just in a trigonometry class, but also in a calculus class, an engineering class, and so on, a different presentation is actually well worth it for us. So here's how we ought to define these. I'm going to put down functions, and to the right, the reciprocal functions. I think folks were mentioning in class already that half of our 6 trigonometric functions are a literal reciprocal of the other half. By reciprocal, we're just meaning swapping numerator and denominator of the fractions. So we'll start off with the originals. Sine of the angle measurement T. Here's T we're referring to, is going to be the second coordinate Y. Cosine, or just cosine, of T is going to be X, likewise. And then from here, there's nothing wrong with saying tangent T is Y over X, and same with all these other 3. But I think it's better to go this way. Tangent t instead of a y over x. Most people, when they're working with this kind of stuff, are going to call it sine of t. That is what y is equal to. Y is literally our sine t. The denominator x is cosine of t. In my opinion, and this is based off actually working with these kinds of problems, that's the better thing to memorize. I would still emphasize these two coordinates. That's always important. But from here on out, define every other four trigonometric functions in terms of sines and cosines, and that is an absolute best practice for this material. Once we have functions, we go to the reciprocal functions, and it means literally what it's saying. You can visualize every one of these as a fraction. So for example, on sine, think of it as a y over 1, or you could say, or sorry, said that wrong. For the sine equals y, think of it as a y divided by 1. Its reciprocal would be 1 over y, like you see right here. But let's redefine that as sine is conflated with cosecant of t. And it's 1 over y, but y is sine t, so it's 1 over sine t. And let me put this little dashed line here, because it's also quite important to know that cosecant is the reciprocal to the sine function. This is a little bit weird. The naming convention doesn't seem like it would make sense. I would have guessed that cosecant is the reciprocal of the cos function, but it's not true. That's something to watch out for. Likewise, move over to the right here. Cosine, when we take its reciprocal, becomes the secant function of the angle t. Looking it up, it's just 1 over x. That is a literal reciprocal of x itself. But that x is a cosine function, so it becomes 1 over cosine t. So we're just about there. Tangent's y over x, cotangent's x over y. So that really is a reciprocal. Down here, let's just take the reciprocal of sine over cosine to say cotangent of t is cosine of t divided by sine of t. So these are our functions finally. And these also have a lot of importance. These must be memorized. And I would say, just as a suggestion of, if you know you're going to take calculus or maybe in an engineering class, physics class, and so on, I would memorize these not just for this course. This is something that you should always have in the back of your head in any class where trigonometry might come up. Because what happens in, say, like maybe a Calculus 2 class, people are just going to assume you know trigonometry, and if a cotangent comes up, we must know, even if we're far removed from trigonometry, we're talking about cosine over sine. Getting foggy on that is going to make the calculus harder when it doesn't have to be, because we'll have too much mental noise of figuring out the trig. Getting it down pat makes everything else you're going to learn beyond this class way, way easier. So we did it, folks. We've defined 6 trigonometric functions. That's not the whole objective of these notes. Next thing, what we'd like to do is just practice evaluating all of them, with an emphasis this time on tangent, cotangent, secant, and cosecant. We just practice sine and cosine quite a lot. But whatever function we evaluate, you are doing sine and cosine, as you see here through these definitions. So that takes us down to example 1, where we'll start practicing some more evaluations. Any questions or comments first? Okay, well, it says to start off, make this a little bit bigger, evaluate the following. I don't always write this down and say instructions for problems, but let's just emphasize here, we want the dead-on exact values. So tangent 11 pi over 6. Here's the first thing we ought to do is place 11 pi over 6. You don't have to put a quick sketch like this. If you have a really good mental chalkboard, you can just visualize in your mind where it is. Me personally, I'm terrible at that. I don't have a very good mental chalkboard. I have to write it out. So I'll start with a unit circle. This one is not good, but let's stick with it just to emphasize that really is okay. Anyone recall where 11 pi over 6 will terminate? Exactly. Right over here is a measurement of 0 radians, or you could think of it as 2 pi radians. If you thought 2 radians, that's also 12 pi over 6 radians. So move backwards by 30 degrees, you're right here at 11 pi over 6 radians. So that's where that one terminates. Next thing I would pick up is values for sine and cosine. Let's use blue and green just to organize. Sine will be blue, cosine will be green. So starting with the sine one, at 11 pi over 6, we project to the y-axis, and that doesn't quite look like a half. Or you know what, it should have been though. 11 pi over 6, if I kind of move it over just the way I would like to, it looks like a negative 1/2 on this one. Then at 11 pi over 6, move upwards. That position here by the green arrow is pretty close to a positive one. So it looks like it would be a √3 over 2. What I would do next if this was a homework problem is try to do it this way without any assists, whatever. That's forcing your mind to really absorb this. But then once you sketch it out, I would definitely, because it's homework, go back to your list of reference angles. Should have copied this one before closing this out. Let's put that down here for our own reference. And just double check if we're in the right ballpark with those two figures. We are dealing with a pi over 6, so we should be using a half for sine and a √3 over 2 for cosine with different signs. So it looks like we've got it. Those are the right values we're going for. Once we have all that, here's the next step we should take. We need to recall that tangent is always going to be sine in the numerator. You know what? If you memorize that half of the information, you're pretty much all set. There'll be sine. And that means the only other function, which is cosine, has to go to the denominator. Actually, let's go down here. So my first step is just to say what tangent is. And I did make a mistake. I was looking at this up here. My function notation is kind of broken though. The input is not t, it's 11 pi over 6. Sorry for that error right there. Let's put in the angle we're actually working with. 11 pi over 6 goes here and here. Then once we get there, we just look up sine 11 pi over 6. That value turned into a negative 1/2 from right here on the unit circle. Divided by the cosine value. Cosine 11 pi over 6 comes out as a √3 over 2. So we have an exact values right here. We still have to simplify this all together, but it's a fast simplification. Notice you're dividing by 2 here and here, so that's just gone. It's negative 1 over √3. You might prefer to write out this way, negative 1/2 multiplied by the reciprocal of the denominator, 2 over √3. And this would equal negative 1 over √3. So if you worked it out that way, I'd say that's terrific. But if you just canceled here, jump to that step, that's okay as well. If you're skipping a good amount of steps for this kind of stuff, it's not trigonometry, it's pure arithmetic, that is okay. Let me put this down just to save on space or put it in a more readable location. Now, once you get to here is where I start to make comments about rationalizing the denominator. My comment is, I really don't care if you rationalize your denominator or not. It's the right answer and it's exact, and it's in a certain sense simplified as well. Nonetheless, there is still value in rationalizing these. You might want to check the back of the book, or you might just want to standardize your answer, and it's just good practice with algebra and arithmetic anyways. So although that is full credit, I'll take the additional step to standardize the answer. We want to eliminate the fact that the denominator is irrational by multiplying by 1. In its form, √3 over √3, one of its many, many different forms. Across the numerator, it's negative 1 times √3. So that's just negative √3. Across the denominator, √3 times √3 is 3. And this is the answer you'd probably see in the back of the book, negative root 3 over 3. To me, that's the simpler answer, but they're both full credit. In chat, Higgins asks, if we rationalize the denominator, would it get marked wrong? No, it would not. So if you rationalized and ended at this problem right here, you'll get full credit. If your work looked like this, sorry, go ahead.
So you mean like if it's already like -1 by root 3 or like minus root 3 by root 3, any answer is okay?
Yep, absolutely.
Okay, thank
So
you.
if you ended right here, that'd be just fine. This one is not the answer in the back of the book, which is a confusion. But if that doesn't bother you, that's absolutely okay. That's for full credit. And this is the one that's also in the back of the book. Makes it a little less confusing if we go for that one. But yes, both are full credit. All the questions or comments at the moment? Okay, well, we've got it, folks. The evaluation of tangent at 11 pi over 6 is that there's actually a little bit of steps on these. And so when you go to work out these, show the steps of working through here for full credit. Well, our goal is to practice a little bit more of these. There's a little bit more on the notes about different properties of the trig functions. So let's take a look at, let me move that out of the way. This thing right here. Secant negative 3 pi over 2. Looks suspicious. Any volunteers for what looks off about that function there? First thing to me that I would be a little bit concerned of is, what is the reference angle on that? Well, there's a 2 in the denominator, for sure. That means we're dealing with pi over 2. It involves a 1 and a 0. That altogether is not necessarily a problem. It could be, though, depending on which thing gets a 0. So looking at a secant, here's where the memorization becomes something that helps us a lot. Secant is a reciprocal function, so it's 1 over something. Any volunteers for which? Is it 1 over sine or is it 1 over cosine?
One over cosine.
Good call. That one is absolutely 1 over cosine. So as Orlando said, we'll go 1 over, now cosine, negative 3 pi over 2. Now, 3 pi over 2 is kind of a special position. That one is going to give you 0 for cosine no matter what. I mean, the problem with that is it lies here. Exactly. You could say not applicable, undefined, does not exist. You're all saying the right thing. This whole thing, well, you could write it down. It's here on digital ink, but it doesn't exist as a mathematical object. Let's take one additional step. Cosine is the first coordinate right here, which is 0. Second coordinate is -1. This then turns into, oh, my hand must have gotten shaky, a 1 over 0, which is undefined. That's kind of a surprise. It's the first time this has happened to us. It'll happen to us a lot more. And it's kind of a feature of these additional trigonometric functions. Sine and cosine are wonderful functions. Their domain is the entire real number line, where we think of those numbers as angles in radian measurement. They are always defined. But the moment we defined functions with a denominator, reciprocal functions, all of these 4 additionally defined functions will have angles at which they're undefined. You could look at the list of reference angles to see where the problems are. Watch out for a pi over 2. A pi over 2 involving a cosine in the denominator, that's either a secant or a cotangent, it's always undefined. And also watch out for anything with radian measurement 0, pi, 2 pi, stuff like that. Gives a 0 for sine, and so where is that bad? You can't have a 0 for sine in your cotangent, nor your cosecant. So there's a lot of values where these things are just undefined. But we'll get pretty fluent at spotting them with all the practice that we're going to be putting in. Any last questions, folks, on our part B here? Okay, looks like we've got 10 minutes. Let's see how much more we can get through. And as far as the organization of the notes go, we'll practice more of these kinds of evaluations because it's kind of like the foundation of trigonometry. All of our work in chapter 5 is find the domain, define all 6 functions, get fluent with evaluating all 6 functions. That's our massive takeaway. So here, that's us practicing doing that. But eventually, we would like to have some formulas. So we're going to work with the Pythagorean identities again. This is possibly coming back on Thursday. And then we're going to look at symmetries. We'll look at odd and even functions, because it turns out cosine is an even function, sine is an odd function, and that's really helpful information for evaluations. So that's what the notes are going to be all about in this section. But let's carry on and work out a few more of these for the sake of good practice. So this time, after secant, let's try a cosecant. For a cosecant, well, we already have a hint here. If you memorize that secant is 1 over cosine, that's great information because it tells you cosecant has been pigeonholed into a 1 over sine. There's no other function to work with here. So this is 1 over sine. I can't put sine t, that would be a mistake. I have to put 5 pi over 6, matching the input that we started with. So 5 pi over 6 would go here. Next thing to look at is the reference angle. We're dealing with a pi over 6 on this one. It's a sine function, so we're anticipating a half, either positive or negative. So let me write it out here. We're expecting a half. But any volunteers from the class in Zoom or in class physically? Would you say it's a positive or a negative?
I think it's a negative.
Negative? Awesome. Let's take a look. So we have a negative 1/2 here. And the only thing we have to do to verify that is, oops, let me try again. Here's our unit circle. 5 pi over 6 goes this way. I think that's one of the angles we started with in class today. And the sine value should be this one right here. Oh, turns out this one will be a positive 1/2 altogether. So let's just go positive, and we've got the right values. Does that make sense to folks on the evaluation here? Awesome. Now that we're starting to do this and do more and more evaluations, you're definitely going to notice a lot of really cool patterns that it gets involved with all this. The more patterns you notice and work with, the easier it gets even still. So let's put down some interesting information about quadrants that could help us out.
Excuse me, like, are we doing it like 1 by 1 by 2? Isn't it like that? Because sine 5 pi by 6. Aren't we dividing?
Yeah. Sorry, what was your question about dividing?
Isn't it gonna be like 1 by sine 5 pi by 6, meaning like 1 by 1 by 2?
I'm not sure what you mean when you say 1 by 2.
Isn't it 2 then? The reciprocal?
Oh, sorry. Yeah, absolutely right. Thanks for spotting that, folks. I think I completely forgot that we're dealing with a sine function here. So this is a reciprocal. And again, thanks for spotting that altogether. I think I probably had a chat to help me out as well. Isn't it equal to 2 since it's 1 divided by 1/2? Sorry, I didn't quite understand what you meant there. I was making a weird mistake on this one. It should have been, let me put this in a color to make it pop. There was a fraction here to here, so it went 1 over, and then this is the mistake. 1/2 goes here. You take the reciprocal of 1/2, and you get 2 altogether. Phew, that one took definitely a group effort to get through. I could tell someone was wrong. People didn't have the most confident look on their face when I wrote just 1/2 right there. Does that help out with that mistake so far, folks? Seeing what went wrong? Okay, so because we started with the reciprocal function, just because we evaluate and throw away the numerator, we've multiplied by 2 over 1 to end on that one there. Phew, that means we finally got that one, and we'll try another one next. Other questions or comments so far, folks? Okay, so here's our next one we'd like to try. This one's a secant. But maybe before even this one, let's put in some extra information about quadrants that you might have already noticed as a pattern, but it's definitely good to put down specifically. Oh, I just turned on sticky keys. That's weird. So here's our pattern with quadrants. So up here in quadrant 1, we're going to have that sine of any angle theta is positive. Might as well write down all the quadrants. In quadrant 2, sine is still positive. Over down here in quadrant 3, now it flips on us. Our sines, wherever we terminate here in quadrant 3, are going to output negative values on the y-axis. So here we have sine of theta is now less than 0 in quadrant 3, and it stays negative through quadrant 4. So quadrant 4, sine theta, less than 0. So that's our pattern. We stay positive through here, then we flip to negative through here. For dealing with cosine, it's a different sort of pattern. The right-hand side are the positives and the left-hand side are the negatives. Or in other words, in quadrant 1, cosine theta is going to be positive. But the moment you move to quadrant 2, imagine your red dot terminates there, cosine takes on a negative angle, or a negative value. So cosine theta is less than 0. We rotate out here, it's still going to output negative. So cosine theta also is less than 0 here. And further rotation, well, now it flipped back to positive. So in this quadrant, cosine theta is suddenly positive again. So if you like quadrants and thinking of sines in those terms, that's a really good way to nail down what should happen with each one of these kinds of angles. Oh, geez, I'm having some struggles with Microsoft Word. Let's move that down. There we go. So we have got another one to try out, secant 5 pi over 3. We're going to go 1 over secant is a cosine function in the denominator, 5 pi over 3. Now let me try this strategy to not make the same kind of mistake as before. If you lead like this, you'll never forget that there's a denominator and a numerator fully in your problem. So that gives us some really great protection. Next, our reference angle is pi over 3. We're dealing with a cosine function, so we're expecting a half. We now need to decide, is that a positive or a negative 1/2 down below? Any volunteers over in person or in Zoom? Pi over 3s are kind of tricky as a pattern.
Is it
Let's
in
put these
quadrant
down.
4?
It would be in quadrant 4, absolutely, which means this one would come out as a positive quantity. Okay, so thanks for specifying that. And 5 pi over 3 is this one. The pattern for memorizing your pi over 3s is kind of like this. It goes 1 pi over 3, 2 pi over 3. But when you flip down, it goes 4 pi over 3, 5 pi over 3. You can memorize this as odds on the right, evens on the left, but it's definitely kind of a weirder pattern to memorize, at least in my opinion. But 5 pi over 3 ended here. We have a value of 1/2 for cosine. As well, that's where the problem sits currently, but we still have work to do. This is equal to 1 times the reciprocal, 2 over 1 for a dead-on 2. We got it, folks? Secant at 5 pi over 3 evaluates to exactly 2 and nothing more, nothing less. Any questions on getting through that one? Okay, well, I have to mention one thing that's kind of weird about our class in trigonometry is, man, it's short. It's just 50 minutes, and it can be sometimes a struggle to find a good spot to end. But today, I think we found it. We have just 1 minute to spare. It's not enough time to start an additional problem. So this is where we're going to come back on our class on Thursday. More evaluations, and then we'll look at the new material on these notes. Any last questions or comments, folks, before we call it a night? Sorry, what was that? Sorry. Oh, yeah, I think you're right. It involves a pi over 2, However, 2 involves a 0, but that's a cosine in the denominator. Good eye on that one. Undefined on part E. Well, have a great night, folks. Thanks for all the participation over Zoom and in person. It helps out a lot. Sometimes these things are group efforts like this one right here. But have a good night. I'll see you all on Thursday.
Thank you.
Okay, thank you.
Thanks, folks. Have a good one.